So chapter 4 starts our study of the graphs of these periodic functions. So before now, we've talked about the values of them, we've talked about the unit circle, and let's apply these to graphs. So there's 5 sections in this chapter. This first section is a little bit lengthy because it kind of gets us started, gets us a basis for all the other chapters. I know, I'm so sorry. So periodic functions are what we're dealing with now. They're called sinusoidal functions or periodic functions. That just means that the periods repeat with a predictable pattern. That's what periodic functions mean. So in real life, tides, phases of the moons, hours of daylight, all of these things can be modeled by sine and cosine functions. The functions are periodic. Again, they repeat in regular intervals or period. So if you look at like a heartbeat, hopefully if you have a normal, non-life-threatening heartbeat, it will look like a periodic function because it's going to repeat the pattern over and over and over again. So let's define a few things. This whole chapter we are talking about periodic functions. You're going to hear me say that a lot. Again, it just means that we will see repeats of these values multiple times. So this function is saying that f of x would be equal to f of x plus n times p. That just means that we are going to be able to see it at multiple points that are a period's distance away from the other values. So like let's say, this high heartbeat is here. Well, if we take the entire period of this heartbeat, we come back to the same high part of the lub-dub of a heartbeat. So we're just going to see repeats of that over and over again. The thing I need you to know here is that the amount of time that it takes to repeat the shape is called the period of the function. That's going to be super huge for us, is to always acknowledge or know the period of the different functions we're talking about. But since this relates to the unit circle for sine and cosine, and since the circumference of a unit circle is 2 pi, it makes sense that sine and cosine functions also have a period of 2 pi. Therefore, sine and cosine functions are called periodic functions with period 2 pi. Feels like I'm repeating myself here, but that's how important it is. So for every positive integer n, sine of x is going to be equal to the same value at a 2 pi distance away. Every 2 pi rotation around the unit circle, sine and cosine will have the same value. So they're going to repeat with different rotations of that unit circle. Now let's talk about what the sine function actually looks like. For most of us, we've seen this before, so it won't be new. But since this sine function is related to the unit circle, its domain is going to consist of real numbers corresponding to angle measures. So we're plugging in angle measures from the unit circle. We're getting out the trig values or the y-coordinates, sine values, on that unit circle, which if we think about the values on the unit circle, our y-coordinates are going to bounce back and forth between -1 and 1. So the lowest it should get is -1, the highest it should get is 1. So when we graph this function, I've got a table of values for x and your sine function. We're going to plot the ones that make sense on this graph. So if we plot 0, 0, bow, there's a 0, 0 right there. If I plot pi over 6.5, so pi over 6 is on your graph, we'll go up a halfway. We're going to skip to pi over 3, and pi over 3 is square root 3 over 2, which for us to graph it, this is approximately 0.866. I just threw that in my calculator to know this, which means we're getting a little bit bigger at pi over 3. But then we get to pi over 2, the value of sine of pi over 2 is 1. Then we're going to make some bigger jumps here. At pi, we are at 0. At 3 pi over 2, we're at -1. And at 2 pi, we're back at 0. When I play connect the dots, one period of the sine function appears. The graph is going to go up, come down, and go back up again, creating a wave pattern. This is called a sine wave. Some things I want us to notice about the sine wave is that since we are at 0, 0, we start at a midpoint or a center line for this graph. And if it's positive, which the normal one is, we're going to go straight up to a maximum before we head to a midline, down to a minimum, and back up to a midline again. So a typical sine function goes from 0 to 1, and then we can continue the wave over and over again. I want us to recognize that it should go to a max first for a normal sine function. The graph of sine, just some attributes about it here. The graph of sine is continuous over its entire domain, and the domain of sine is going to be from negative infinity to infinity. We can go to all of the points here. The x-intercepts have x values that will repeat every 0 plus pi times n, where n is an integer numbers, meaning the first x-intercept I see is at 0, 0. And then I travel a distance of pi, I see another x-intercept. I travel a distance of pi, I see another x-intercept. So starting at 0 and every pi distance away is another x-intercept.
So what goes in n?
Any number. So you could put like 5. So 0 plus 5n would be, 0 plus 5 times pi would just be 5 pi. At 5 pi, you would find another x-intercept. Like if I zoomed this graph out, at pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, every repeat of that, there will be an x-intercept because it'll repeat over and over again. The period of the sine function is 2 pi. That's how long it takes to complete the shape from 0 up, down, back to a 0. Since we can rotate it around the origin and it looks the exact same, this means that the function is an odd function. For all x values in the domain, if you plugged in a negative x value, you'd get the opposite sine value, which is we'll deal with this later when we do identities. That's where this comes in handy, but it is a part of this function itself. This picture down here at the bottom is not really necessary for you to understand what it's saying, but it's just, again, showing you where these values come from. Since I only showed you a table of some values, it's saying, look, at 0, we have 0. At an angle measurement of pi over 6, we're at height 1/2. At an angle measurement of pi over 2, we're at a height of 1. And as we continue going around the circle, so a further angle value is a smaller output value. So that's how the values go up, and then they go down, and then they go up again. So this shape comes from the vertical distance around this unit circle, is where this is coming from. What I need you to know, again, is that sine starts at a middle, goes to a max, then a middle, then a minimum, then a middle. So it should go up first. Now it has a related function, a graph that's going to look very similar if we flip it over. Cosine function is also related to the unit circle, but with the cosine function, it's going to correspond to the x coordinates around the unit circle. So we're still having an input of angle measurements and an output, this time of the x coordinates, but our x coordinates also just go from -1 to 1. So from a left distance of -1 to a right distance of 1. If again we plot these points that I'm giving to you in this table, which you would have been able to tell me, because you've been telling me this table for a while, we have 0, 1, which means the first part of this cosine graph is going to be at 0, 1. At pi over 6, we have square root 3 over 2, which again is approximately 0.866. So if we plot approximately 0.8, it's here-ish. I don't see pi over 4 on my graph, but I do see pi over 3. That would be 1/2. Pi over 2 would be 0. And then I'm going to start jumping around. So at pi, we go to -1. At 3 pi over 2, we go to 0. And at 2 pi, we go back up to 1. So playing connect the dots here, my graph looks something like this. This is the cosine wave. And it would continue to make this shape if we kept scrolling on Desmos or kept scrolling on our calculators over and over again. For the cosine wave, we start at a maximum, go to a middle, then to our minimum, then our middle, and then back up to our maximum. Those are the things I want us to recognize about the cosine function, that it starts from the top and immediately starts going down until it comes back up again. Some facts about cosine here. It is also continuous on the entire domain from -infinity to +infinity. So all real numbers. You can plug any angle value in there and it will work. The x-intercepts have x values of the form pi over 2 plus pi times n. And the way that this comes from is because I see the very first positive x-intercept occurs at pi over 2, and then it takes me a distance of pi for another x-intercept to show up. If we kept scrolling on this graph, another pi distance away, there would be another x-intercept. So there are multiple of them every pi distance away, starting at pi over 2. Since this shape goes back up to a maximum at 2 pi, it has a period of 2 pi. I can fold this one along the y-axis, and it would land right on top of each other. That's how it's symmetrical, which means it is an even function. And again, to get us used to seeing this notation when we get into identities, it's important. But if you put a negative angle in for cosine, it returns the same as the positive input for cosine. Now, what is important to notice, and I've graphed both sine and cosine for you. I highly recommend highlighting it. I'm sure some of us highlighted our graphs on our page as well. The one that is dashed is sine, so I'm going to use the color I used for sine just so you can see it. I've graphed it from 0 till almost 4 pi, so we're seeing 2 waves of it, or a wave and a half, I guess. And then this one that is solid is cosine, just so you can use the same colors for your brain here to see the difference. They look the same, they're just shifted from side to side. So the graph of cosine, my blue function, is the same as the graph of sine function, although it is shifted to the left pi over 2 units. Meaning, if I look at sine and find this first maximum, I would find the first maximum of cosine pi over 2 units to the left of it. The first 0 for sine, I guess technically the second since I'm not including 0, is just pi over 2, pushing it to the left. And every single important point for sine, if we push it to the left pi over 2 units, you are going to exactly find the same value for cosine. Can't really see that one because it's off screen, but that just means for us that these two functions are related to each other just by a horizontal transformation. Shifting it to the left a little can make a sine function into a cosine function, which is really interesting. But of course, the sine and cosine function themselves are never always just going to stay nice and pretty going between -1 and 1. We can have higher frequency graphs, we can have lower frequency graphs, we can have taller graphs or smaller graphs, and all sorts of transformations. Let's talk about what sort of transformations we can apply to these graphs. The first one is called the amplitude of the graph. When we are adjusting the amplitude of the graph, we are talking about the distance, or half the distance, between the maximum and minimum values. It describes the height of the graph above and below the horizontal middle line. So you can think of it as the height of a peak or the depth of the valley for each of the sine and cosine waves. When you take a number and you multiply it in front of sine or cosine, that number is telling you how much you are stretching or shrinking that graph. So that becomes my amplitude. It is just going to be the absolute value of it, because if that number is negative in front of the function, it's a reflection over the x-axis, not anything to do with the amplitude. So our range will change. It will change from -1 to 1 to negative absolute value of A to absolute value of A. So let's see here. What's going to happen to the graph of sine, which I've plotted for you, that's regular sine, when we decide to graph 2 sine of x. Okay, so we are going to graph 2 sine of x on this interval. That means instead of having a maximum value at 1 and a minimum value at -1, I'm actually going to have a stretched out. Yeah, so instead of having those maximum and minimum values at 1, I'm going to put them at +2 and -2. So I've taken my sine function, I'm going to draw it in red, and I have just stretched it up and down, causing a higher amplitude. I can do better on that drawing. Let me try again. Still crossing through all the same x intercepts, but just making the height and the depth bigger. So when we compare it in words to the graph of sine of x, and this is a little sentence moment for us, we would say the graph of y equal 2 sine of x is a transformation language vertical stretch, because it's stretched out, by 2 of the graph of y equals sine of x. It is a vertical stretch by 2. It's gotten taller and lower. Therefore, it has a range that is changed. This one has a range of -2 to 2. A typical sine function has a range of -1 to 1, as you see in the graph. But since we've multiplied our function by 2, we've stretched it out, so it has a higher or lower range from -2 to 2. So numbers in front of the function are going to stretch and or shrink, making it taller and or smaller. Another thing we can change on a function is that function's period. Now we said on the first few pages that the period is the amount of time, I'm always going to say time because that's just my habit, the amount of input values or time it takes for the function to repeat itself. So if we take a number b and we multiply it, this time it is inside the sine or cosine function. Notice it's inside, not in front of. It's going to create either a horizontal stretch of the graph when that b value is a fraction, or a horizontal shrink when b is greater than 1. But what is important here, what I want you to know, is that the period of these functions will change if you have a b value in the function itself. So if I have a b in either sine or cosine, so I'm multiplying by a b number inside the function, the period is no longer going to be 2 pi, it's going to be 2 pi divided by that period. This is huge, like this is a moment for us. Maybe put like a whole little exclamation point here. The period will be 2 pi divided by b. Okay, so now we're going to do the same thing like we did in example 1. We're going to graph cosine of 2x on the interval from -2 pi to 2 pi and compare it with the graph of cosine of x. I've graphed cosine of x for you. We're going to graph cosine of 2x. So this requires just a little bit of work. Let's figure out the new period for this function. The period is going to be 2 pi divided by b. What's the number that is plugged into this formula for b? 2. So we are going to figure out that the period of this function is 2 pi divided by 2, which means that the new period of this graph is just pi. So we should finish an entire cosine shape from maximum to maximum, not in a 2 pi distance, which is what's shown on your graph, but in the distance of pi. So if I'm plotting some new points for cosine here, and I know it's blue already, so I'm going to use green, I would have a maximum appearing at 0. The next time I should have a maximum is at pi, which means the next time I have a maximum should be at 2 pi. If I work the other way, I should have a maximum at -pi, and I should have a maximum at -2 pi. Since we know this shape has to start up, go down, come all the way back up, that means I'm going to have my minimum value at pi over 2, and at 3 pi over 2, and at -pi over 2, and at -3 pi over 2. When I play connect the dots here, kind of looks like a piece of DNA, but it's not. This function is occurring more frequently. It has a higher frequency than the regular cosine function. So if we're comparing it, not using the word frequency, but using our transformation language, we would say the graph of y equal to cosine of 2x is a horizontal shrink by a factor of 1/2 of the graph of y equals cosine of x. So two things I want to point out by what I wrote. It's shrinking because if you actually look at the graph, I took that blue function and I squished it in to make it happen more often. This is where horizontal shrinks are not actually confusing. Shrinking, getting smaller, it's coiling faster. But where did those 1/2 come from? Because the number that's in the function is 2, so why did I write down 1/2? It is under 2 pi, yes, that's kind of what I'm thinking because I'm taking the period and dividing it by 2. But when we learned horizontal transformations back in like Algebra 2, we always took the horizontal number and we flipped it to its reciprocal. This is really the first time visually it makes sense why. Because you are dividing by b, it's 1 over b for your transformation. In my mind, the horizontal stretches and shrinks make sense with sine and cosine the best of all the functions we learned them for. So next up, we're going to be graphing sines and cosine functions from start to finish that may have a mix of an amplitude change, a reflection, as well as some sort of period change. And so the book defines some really good guidelines for sketching these sine and cosine functions. If you have taken trig before in pre-cal or in another way and you know a different way to graph sine and cosine, I'm totally fine with it. But this book lays out some really great guidelines. It says if we're going to graph these, we're going to first start by finding the period. That's really where you need to start every single time, is finding that period 2 pi divided by b. And you're going to lay off on your x-axis a distance of your period. So we'd go from 0 to whatever the period is on our graph, because we're putting the tick marks on our graph. I don't have any graphs here that already have tick marks for you, so you have to put the tick marks. Speaking of those tick marks, though, you're going to divide this subintervals into 4 equal parts. So you want there to be 4 spaces between 0 and your number for the period. You're going to evaluate the function for the 5x values, so 0 and your 4 equal parts in step 2. These points will be the maximum, the minimum, and the x-intercepts, or your middles. Then you're going to plot the points found in step 3 and join them with a curve having the correct amplitude, and voila, we have graphed the function. Let me walk you through a couple, and again, I'm going to walk you through filling out this table, which is the guidelines that the book sets out. I really like them. If you know of another way to graph trig functions that makes sense for you, I'm cool with you using it as well. Now this function, we are graphing y equal to -2 sine of 3x. We're just going to do one period, and we're going to use the guidelines above. First things first, what is the period of this function? It's going to be always 2 pi divided by over 3, because we're dividing by 3, because the 3 value is inside the sine function. Before we move on, what is the amplitude? 2. I'm going to put 2 and I'm going to put a little comment. I'm going to say, but it's been reflected. So remember, amplitude is the absolute value of the number in front of the function. We just need to make sure that we remember this function should be reflected since that number is negative. The amplitude is 2, but in my mind I'm thinking 2, but it's reflected. Don't forget. So we lay off a distance on our x-axis from 0, boom, there's 0, all the way to 2 pi over 3. You're deciding that's the distance. That also, 2 pi over 3, becomes the last number in the first row of this table I've set up for you for x values. We need to split this number line into 4 equal parts. Easiest thing to do is take it and split it into 2 equal parts first. What is halfway between 0 and 2 pi over 3? 1 pi over 3. So in the middle of my table and in the middle of my graph, I put pi over 3. I still need to have 2 more spots, so I'm going to put a halfway distance between 0 and pi over 3. What is that distance? Pi over 6, because half of pi over 3 is pi over 6. Now what would this tick mark be in between pi over 3 and 2 pi over 3?
Pi over 2.
Pi over 2. Okay, we've got our table. We're ready to roll. Our table is going to start on the inside of the function. So it says x, which are our distances on the x-axis that we lay out. But then it says to do 3x. I'm getting this 3x from the problem. It's the argument of the function, so 3x. We're just going to take these numbers and multiply them by 3. 0 times 3 is 0. Pi over 6 times 3 is 3 pi over 6. But 3 pi over 6 reduces to pi over 2. 3 times pi over 3 is just pi. 3 times pi over 2 is 3 pi over 2. And 3 times 2 pi over 3, 6 pi over 3, which is 2 pi. Okay. Notice that the angles we have now written down in the second row are all of the quadrantial angles. Yes? What is the sine of 0? What is the sine of pi over 2? What is the sine of pi? 0. What is the sine of 3 pi over 2? -1. What is the sine of 2 pi? 0. So those numbers come from my quadrantial angles. But I don't just want those output values because, again, I have an amplitude number here. So at the very end, we're going to multiply these numbers, sine of 3 pi times -2. 0 times -2 is still 0. 1 times -2 is -2. And then we have 0. And then we have +2. And then we have 0. This last row here is what I would get as an output for -2 sine of 3x with the x values that I chose showing one period of this function. So we plot these points. I need to go up a value of 2 since I know that this goes up to an amplitude of 2, and I need to go down to an amplitude of -2. So at 0, I say 0. I got my point. Let me make that red. At pi over 6, it says to go to -2. At pi over 3, it says to go to 0. At pi over 2, it says to go to 2. And at 2 pi over 3, it says back at 0. When I play the connect the dots here, again, we're only graphing one period of this function. Then we give ourselves a quick check. Does the function have an amplitude of 2? Yes. It goes up or down 2 units. Is it reflected? Yes, because sine normally goes from 0 to a maximum. This time we go from 0 to a minimum, so it's been reflected. And then does it have the correct period? Did you start and finish one whole wave between 2 pi over 3? Yes. Yes, you have graphed the function.
How do we remember doing this?
We did it differently last year in my class. We did something called an x increment. Same thing, because I told you to take the period, divide by 4 for your x increment, and count by that, but I made you do it way more complicated before.
Yeah, you made our lives more complicated.
Yeah, it was that homework assignment last year where there was like 18 pages of graphs,
Yeah.
only because it required so much space. How do I what? Say that again? B is the number inside the sine function. So B is always going to be like, if it's sine of something x, whatever that something is your B value.
So not in front?
Not in front. In front is A. Yeah, A is amplitude, it's in front. B it affects your period, and it's inside.
Wait, how come you do that? Wait, I don't know if this is a stupid question. But you said A is, wait, hold on. How do I do this? So that is the amplitude, right? So why did you put 2 as well?
It's always the absolute value of the number here. So amplitude is always a positive number. I just wrote, and that's why I wrote the word reflected around it or next to it, because in my mind, I like to know the amplitude is 2, but I also want to remember that it should start down because it's reflected. This negative in front affects a reflection over the x-axis, not the amplitude. That was a great question. All right, example 4, let's do it again. This time we're graphing -3 cosine of pi x for one period. First thing we do always is find the period of the function. This is going to be 2 pi divided by what? Pi. Because we're looking at this function, we look for the number inside the cosine function. It's pi. Well, what is 2 pi divided by pi? 2. So that means to me that the very last number I should have in my table and the last number I should have on my graph is the number 2. All right, let's find our amplitude. What is the amplitude of this graph? 3, but again, this one's going to be reflected. The negative does not affect the amplitude, but it is a reflection of this graph. I like to write that down for myself so I remember it shouldn't be starting at a maximum, it should be starting at a minimum. Okay, following the guidelines, we have 0, we have 2. I need 4 intervals in between it. It's always easiest just to start in the middle. What is half of 2? 1, so that goes in the middle. What is half between 0 and 1? Yes, I'm going to use a fraction. 1/2, but yes, 0.5. And what is halfway between 1 and 2? 3/2, or 1.5. But again, I'm going to use the fraction on purpose because I think it helps us in a little bit. Now my next row, once I have these 5 numbers here, or the 4 subintervals, I'm going to do pi times that number. What is pi times 0? What is pi times 1/2? Pi/2. This is why I left it as fraction. Pi times 1 is pi. Pi times 3 pi/2. Wow, I just said the whole answer. You get it. 2 times pi is 2 pi. Oh, snap. What do you notice now is the same here and here? They're still my quadrantial angles. That's what's happening every time. So this next row should be really easy to figure out. For cosine, my quadrantial angles are cosine of 0, which is 1, cosine of pi/2, which is 0, cosine of pi, -1, cosine of 3 pi/2, 0, cosine of 2 pi, 1. Those are the quadrantial angles that we've known for a while, hopefully. But because this function has an amplitude of 3 and it is reflected, we're going to take those numbers and multiply them by -3, which means this is actually -3, 0, +3, 0, and -3. When we graph this one, to include the amplitude, I give 3 little tick marks and label it 3 and -3. And I start plotting my points. When an x is 0, the output was -3 based on my table. When the input was 1/2, my output was 0. When the input was 1, my output was 3, and then 0, and then back to -3. So my cosine wave will look like this. And we give ourselves a quick check. We check amplitude and period. Did we have an amplitude of 3? Yes, because the height of my wave, bop, 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 is 3. Oh, I almost missed that dot. Do I have the correct period? Is the period go from 0 to 2 to complete the entire shape? Yes, so we have the correct period. Only because typos bother me, I'm going to point one out to you. It does not affect anything. This right here, this title, we're not graphing a sine function. This should say cosine.
I have a question.
Yes.
Since this we're graphing like a period, is it still 2 pi? Like this is a 2 pi, like 1 period?
That's a great question. So a regular cosine and sine function finishes shaped or has a period of 2 pi. Because we have changed this number, the b number, our period has been shortened, has been changed. So it's not going to have the same period. It's going to have a ratio of that period, which is why we do 2 pi divided by this number.
So this is 1 period for this graph.
Correct. If I had actually put 2 pi on here and made you shrink it up, you would see that it doesn't reach 2 pi. But we're just creating our own numbers here on this number line to show 1 period. Any other questions before we move on? Okay, example 6. It says determining an equation for a graph. So if I give you a picture of a graph, we should have the skills to be able to determine the entire equation for it. We'll add more complications as we keep going. But determining an equation for this form, I don't know right away, or it didn't tell me right away, if it's sine or if it's cosine. But if we look at this graph, does it resemble a cosine wave or a sine wave? Cosine. Why does it resemble cosine?
Because it doesn't start at 0.
Correct. Sine should start at a midline of 0. Since this one starts at, well, it starts at a minimum, but since it starts at a maximum or a minimum, it is probably a cosine function. So again, we're going to pick this one, and just because it's your notes, let's write a note to ourselves. Since it starts at a max/min, normally should be a max, it is cosine. It will. We won't do that till next class. We can vertically translate it up and down. And we can horizontally translate it, but we won't do that till later. Okay, since we know it's cosine, that means we only need to figure out what the A value is and what the B value is so that we can plug them into the formula. A should be easy because two ways we can find it. Number one, we can look at the graph. From the middle of the graph, how many steps do I have to take to get to a maximum? 2. So we know that A is going to be 2. If you couldn't tell on this graph or it was some sort of word problem, the amplitude is found by the maximum value minus the minimum value divided by 2. So just to show you two ways here. What is the maximum value of this graph? The max it goes to is 2. What's the minimum it goes to? Oh, but negative. Yeah, that's the word it. Sorry. You're right. That was not the full word it. So if I do 2 minus negative 2, that's like 2 plus 2, which is 4. 4 divided by 2. Either way you see it, if you can visualize it on the graph of seeing that the height of the crest, that's the technical word for it, the height of the crest is 2, or the depth of the crest is 2, then you have an amplitude of 2. But in a word problem, when they don't give you a formula, it's good to know that, or when they don't give you a graph, it's good to know that formula. Ooh, but now we need to find B. Interesting. The formula I gave you for B originally, I said that the period would be equal to 2 pi divided by B. But I want to find B. So we can rewrite this formula, switching the location of B and period the same way you do for like distance, rate, and time, that little triangle of distance, rate, of time, multiply by B, divide by period. We know that the B value is also 2 pi divided by the period. Period is something we can see from the equation or from the graph. How long does this function take to go from minimum to minimum? 4 pi. So this is going to be 2 pi divided by 4 pi, which when I reduce that fraction is what? 1/2. Again, if you're like, whoa, where'd this 4 pi come from? Great question. Can y'all read that? Let me try that again. That's how long it takes for me to go from minimum to minimum. Okay, so we have the B value, we have the A value. That's all we need to write this equation. Oh my gosh. We would say that this equation is y equal to 2 cosine of 1/2 times x. But I'll tell you right now, if we graphed that, it wouldn't return the same picture. What have I forgotten? Look at this picture. Remember, cosine normally starts at a maximum. What does this one start at? So what do we need to do with this? Flip it, reflect it. So we're going to make it negative. So it should be -2 cosine. This is what is going to be tricky with these because amplitude only tells you the height and depth of the crest. It doesn't remind you that it's reflected, which is why I always wrote that word next to it on the other pages. So always make sure at the very end to double check that it's not been reflected. That's the thing I always messed up as a student, which is why I aggressively write the word reflected next to things now. Okay. Fabulous. If you haven't gotten a calculator today, make sure you go get one because this next one we're going to use our calculator to see these functions a lot better because a typical calculator setup doesn't really give us a good view of sinusoidal or periodic functions. So a trigonometric model, sine and cosine functions can be used to model a lot of real-life phenomena that repeat their values in a cyclical or periodic manner. Average temperature in a certain geographic location, is one such example. That makes sense to us. It's hotter in the summer, cooler in the winter, hotter in the summer, cooler in the winter. It's going to repeat over and over again as time changes. So the average temperature in degrees Fahrenheit at Mold Bay, Canada, which I Googled it, it's like way up there, okay, way north, can be approximated by this function. F of x equal to 34 sine of pi over 6 times x minus 4.3, where x is the month and x equal 1 corresponds to January and x equal 2 corresponds to February, and so on and so on and so on. So where x's are our months. We're going to observe this graph over a 2-year interval to graph in the window from 0 to 25 by negative 45, 45. The reason I'm having us do this is if we were to just graph this function in the regular like y equals on our calculator and press go, we likely would not see this function or see any interesting things about this function because your calculator starts the window at negative 10 to 10 and negative 10 to 10. We need to see the actual information for this graph. So follow along with me. We're going to go to y equals. We're going to type in that entire function. So 34 sine of open parentheses and then alpha y equal inner pi divide by 6, open parentheses, x minus 4.3, close. I'll give you a second. I typed really fast. This problem wants us to look at 2 years, which is from 0 to 24, since these are our months, but we're going to go from 0 to 25 so we see the full thing. And then from negative 45 to 45, remember degrees-wise in degrees Fahrenheit. So negative 45 degrees, terrifying, absolutely not, never living there, to 45 degrees. So we go to window. It's a button in the gray part of your calculator. You may have never used this before, but we should get used to it. We're going to adjust the x minimum, x maximum, y minimum, and y maximum to the settings in the problem. And those are right here. So these settings go in order. X min, x max, by the y minimum, y maximum. So we'll type in those numbers, 0 and 25, and then negative 45, 45 in the appropriate parts. Let me show. So now that we've seen it on our calculator, let's sketch that on our graph here that I've given to you. So it's going to go like this and then up. Doesn't have to be perfect, but just so you see. Oof, that's real bad. Let me try that again. Just so you see all the 2 periods of this function. Please forgive my ugly drawing. Now, Devani made a good point. She just said it kind of looks like a cosine function because it did not start at the middle. I hear you, but this has been shifted to the left or right, which we will actually talk more about next class. So this number that's inside next to the x, not multiplied, but added and subtracted, has shifted it sideways by 4 months. So if we actually look at 4.3, that's where the midline is. So if you look at your graph just a little bit past 4, that's where your midline is. That's because we've moved it just a little bit past 4 to adjust for what time of the month it was, or what time of the year it was. We'll discuss more about this, called phase shifts. Preview. We'll discuss more about phase shifts next class. So the period here, let's figure out what the period is. Kind of hard to tell from the graph because on here I still don't have very good numbers. So I'm going to go back to the formula itself. We know that the period is 2 pi divided by b. This time, the period, or the b value, sorry, is pi over 6, right? That's the number inside of the sine multiplied by x. So if I flip this, keep 2 pi, change the divide to multiply, and flip the other fraction, this becomes 12. The pi's will cancel. 6 times 2 is 12. Now, does that make sense? What are we modeling here? Months. So if our period is a year, does that make sense? 12 months, 1 year. That makes sense. That's about the time our temperatures start repeating every year. The amplitude of this graph, what is the amplitude? 34. That's the height of the crest or the depth of the crest, the height of the hill or the depth of the valley. We're getting that from the function itself. Now, this question goes on to ask, according to this model, what is the average temperature during the month of May? Here's a function we may have never used on our calculator. See what I did there with the May? We can actually trace this function value using not like any fancy things on our calculator. First things first, the month of May. What x value is it for this scenario if the month is May? 5. So if I know that May is equal to 5, I'm really asking you to find f of 5. Now, I 1000% know that you know how to evaluate functions, and you could just take that number 5 and plug it in. But you already have the graph on your screen. So you're going to use the trace function of the calculator to figure this out. While looking at a graph, press trace, which is in the gray buttons. Then type the value you want to evaluate, which for us is 5, and then press enter. So if I was doing this, I'd go from looking at our graph, that f of 5 would be approximately equal to 12.18 degrees Fahrenheit. Is that the number you guys had on your screen? And we can do that really quickly on here just by pressing trace 5. Now remember, can you imagine it being May and it is 12 degrees outside? Yuck. I'm sorry. No, thank you. That's true. We have the opposite where we're at 117 at that point. No, I'm just kidding. I'm not wrong. Last question for today. It says, what would be an approximation for the average annual temperature at Mold Bay? If we just think about what average annual temperature is, like when you take an average of stuff, what are you normally doing? Adding them up and dividing by the number of things that you add up. So you're looking for like the middle number, right? What's the middle of our graph? Isn't our graph centered around the x-axis? So our annual average temperature, our midline, which is what that's asking for, is 0 degrees Fahrenheit. So absolutely not, I'm never living here, if that's the average temperature throughout the year. No, thank you. Give me the 110, please. Not really, Mother Nature, not really. I'm sorry. Y'all can all blame me if that happens this summer. Actually, please don't. Please don't. Don't text me. Okay, so that's our first section of chapter 4. Like I said, we're going to continue to add skills with graphing. Next class, we're going to talk about moving them left and right and up and down. And then we'll start discussing the tangent and cotangent graphs, secant and cosecant graphs, and what they are used for, which is cool physics stuff.